Welcome, everyone. Tonight, we're embarking on a journey to uncover the hidden wonders of the cosmos, things that often go unmentioned in standard lessons. Prepare to have your understanding of space expanded as we dive into 10 things your teacher never told you about space. This slide serves as a captivating introduction to the unexpected realities of our universe. Imagine a place where silence reigns, yet the vacuum itself holds a distinct aroma, often described as a mix of hot metal, ozone, and even walnuts. Picture astronauts, free from Earth's gravity, actually growing taller as their spines decompress. Consider how space, despite its reputation for cold, features extreme temperature contrasts, with scorching direct sunlight next to frigid shadows. And truly astounding, the cosmos is home to colossal clouds of alcohol, a testament to the bizarre and beautiful chemistry at play. These are just a few teasers of the incredible, often counterintuitive facts we'll explore, inviting you to see space not just as a vast void, but as a realm brimming with astonishing secrets and phenomena. The empty void isn't empty at all. Space is fundamentally far from an absolute vacuum. Firstly, it contains the interstellar medium, a pervasive, extremely sparse mixture of gas, predominantly hydrogen and helium, and microscopic dust grains. These seemingly empty regions are, in fact, the nurseries where new stars and planetary systems are born. Secondly, the universe is dominated by constituents we cannot directly observe: dark matter and dark energy. Dark matter, accounting for approximately 27% of the universe, provides the gravitational scaffolding for galaxies and galaxy clusters. Dark energy, making up about 68%, is responsible for the accelerating expansion of the cosmos. Their presence fundamentally shapes the universe's structure and evolution. Furthermore, space is continuously permeated by the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang itself, a relic electromagnetic signature from the universe's infancy. Finally, a constant flow of subatomic particles, including high-energy cosmic rays originating from supernovae and black holes, and billions of elusive neutrinos, silently streams through every cubic centimeter of space, even passing through us constantly. Thus, the cosmos is a vibrant, dynamic environment teeming with known and unknown components. Our perception of empty space as a void is profoundly incomplete. At the smallest scales, below even atoms, the vacuum of space is not truly empty, but a bustling, chaotic realm known as quantum foam. Imagine the very fabric of space-time constantly bubbling and fluctuating like the surface of a boiling pot. Within this quantum foam, virtual particles and antiparticles spontaneously manifest, existing for incredibly brief moments before annihilating each other. These fleeting entities borrow energy from the vacuum itself, adhering to Heisenberg's uncertainty principle, allowing them to appear and disappear in pairs. This incessant subatomic activity is not merely theoretical. It has measurable effects, influencing fundamental forces, contributing to the vacuum energy, and playing a role in phenomena such as Hawking radiation around black holes. It reveals a universe far more dynamic and alive at its most fundamental level than we typically conceive. Dark matter and dark energy represent the universe's invisible majority, fundamentally shaping the cosmos. Dark matter, comprising approximately 27% of the universe, acts as an unseen gravitational scaffolding, holding galaxies and galaxy clusters together. Its presence is inferred through its gravitational effects on visible matter and light, as it does not emit, absorb, or reflect electromagnetic radiation. Dark energy, an even more elusive component, makes up around 68% of the universe. This mysterious force is responsible for the accelerating expansion of the cosmos, pushing galaxies further apart at an increasing rate. Unlike dark matter, which clumps, dark energy appears to be smoothly distributed throughout space. Together, these two invisible components dictate the fundamental structure and evolution of the universe, yet remain among the greatest enigmas in modern astrophysics, challenging our understanding of cosmic composition and dynamics. The universe is not expanding into pre-existing empty space. Instead, space itself is actively stretching, increasing the distances between all galaxies. This expansion is uniform across the cosmos, meaning there is no central point from which everything is moving away, nor is there an outer edge to reach. Every observer, regardless of their location, would perceive all other distant galaxies receding from them. This concept is often likened to the surface of an inflating balloon, where dots drawn on the surface move further apart as the balloon inflates, yet no dot is at the center, and the surface itself has no boundary. Therefore, the universe presents itself as fundamentally unbounded. Cosmic redshift is a fundamental observation in astrophysics, revealing the expansion of our universe. As light from distant galaxies travels across the cosmos, the fabric of space itself stretches. This stretching effect elongates the light waves, shifting them towards the red end of the electromagnetic spectrum, much like the Doppler effect for sound waves. The greater the distance to a galaxy, the more its light is redshifted, indicating a faster recession velocity. This direct relationship, known as Hubble's law, provides compelling evidence for the Big Bang theory and the continuous expansion of space. This expansion also defines our cosmic horizon, the boundary of the observable universe. Light from objects beyond this horizon either has not had sufficient time to reach us since the Big Bang, or the space between us and those objects has expanded so rapidly that their light will never reach us. Understanding cosmic redshift allows us to measure distances to galaxies, calculate the universe's expansion rate, and ultimately trace its history. Stars are not merely distant points of light. They are the universe's colossal foundries, driven by immense gravitational pressure and extreme temperatures. Within their cores, nuclear fusion acts as a cosmic forge, transforming lighter elements like hydrogen and helium into progressively heavier ones: carbon, oxygen, nitrogen, and all the way up to iron. This process, known as stellar nucleosynthesis, is fundamental. Every element heavier than hydrogen and helium found on Earth, including those comprising our own bodies, was initially synthesized within the heart of a star. When these massive stars reach the end of their lives, they often explode as supernova, scattering these newly forged elements across the galaxy. These enriched stellar remnants then become the building blocks for new generations of stars, planets, and ultimately, life itself. Stellar nucleosynthesis is the profound process by which stars create every element heavier than hydrogen and helium. These lightest elements were primarily forged during the universe's infancy in the Big Bang. Within the incredible pressures and temperatures of a star's core, atomic nuclei are fused together. This process commences with hydrogen converting into helium, subsequently forming carbon, oxygen, and progressively heavier elements, culminating at iron. This fusion constitutes the energy source that allows stars to shine for billions of years. When exceptionally massive stars exhaust their nuclear fuel, they undergo a spectacular and violent supernova explosion. These explosive events generate the extreme conditions required to synthesize elements heavier than iron, such as gold, silver, and uranium. The remnants of these supernova, enriched with newly forged elements, are then dispersed throughout the galaxy, eventually contributing to the formation of new stars, planets, and fundamentally the building blocks of life itself. Each atom in your body, with the exception of primordial hydrogen, was once forged either in the heart of a star or in its explosive death. Supernova remnants represent the aftermath of the universe's most powerful stellar explosions. When a massive star reaches the end of its life, it collapses and then rebounds in a supernova, an event so energetic it outshines entire galaxies for a brief period. Crucially, these explosions are the sole natural factories for creating elements heavier than iron, including silver, gold, and uranium. Without supernova, these vital elements, which form the bedrock of planets and life, would not exist. The expanding shock waves and debris from a supernova, known as a supernova remnant, then disperse these newly synthesized elements across interstellar space. This vast cosmic recycling process enriches the interstellar medium, providing the necessary raw materials for the formation of future generations of stars, planets, and ultimately the complex chemistry that leads to life. Every atom of gold in jewelry, every iron atom in our blood was once forged in the heart of an ancient, exploding star. Beyond the common misconception, black holes are far more than mere cosmic vacuum cleaners. They do not actively suck objects in. Rather, their immense gravitational pull means anything that crosses the point of no return, the event horizon, cannot escape. These colossal entities are fundamental to the universe's structure. Supermassive black holes, residing at the hearts of most galaxies, including our own Milky Way, play a pivotal role in galaxy formation and evolution, acting as gravitational anchors that influence the dynamics of billions of stars and gas clouds. Furthermore, the intense gravitational and magnetic fields around them can power incredibly energetic phenomena. From their accretion disks, where matter heats to millions of degrees, powerful relativistic jets of plasma can erupt, spanning thousands of light years. These jets contribute significantly to cosmic feedback, impacting the distribution of gas and the rate of star formation in their host galaxies. Their extreme gravity also causes gravitational lensing, a phenomenon where light from distant objects is bent and magnified, providing unique insights into the universe's most remote regions. Thus, black holes are not just destroyers, but architects and engines of cosmic evolution. The concept of an event horizon defines one of the universe's most profound boundaries. It is the theoretical perimeter around a black hole, marking the precise point where the gravitational pull becomes so immense that the escape velocity required to leave it would exceed the speed of light itself. Once anything, whether it be matter, energy, or light, crosses this threshold, it is irrevocably committed. There is no turning back. It has reached the ultimate point of no return, destined to be drawn deeper into the black hole's singularity. The event horizon is not a physical surface, but a profound warping of spacetime, effectively isolating that region of space from the observable universe. Black holes are often imagined as eternal cosmic prisons, but Stephen Hawking introduced a revolutionary concept, Hawking radiation. This theoretical emission suggests that black holes are not perfectly black. Instead, they emit a faint thermal glow. This phenomenon arises from quantum mechanical effects near the event horizon, where particle-antiparticle pairs spontaneously appear. When one particle falls into the black hole, its partner can escape, effectively carrying away a tiny bit of the black hole's mass energy. Over immense cosmic timescales, this continuous loss of mass leads to the black hole's gradual evaporation. The implications are profound. Black holes, even supermassive ones, have a finite lifespan, ultimately disappearing from existence and challenging our fundamental understanding of spacetime and quantum mechanics. Beyond the simple concept of orbiting, planets engage in two fascinating and profound processes: migration and tidal locking. Planetary migration describes the phenomenon where a planet's orbital distance from its star can change dramatically over cosmic timescales. This often occurs during the tumultuous formation of a solar system, as gravitational interactions with the vast, swirling protoplanetary disk of gas and dust, or with other massive planets, can cause worlds to spiral inward towards their star or drift further outward from their birthplaces. Our own solar system's architecture may have been sculpted by such events. The second phenomenon, tidal locking, is when a celestial body's rotation period becomes synchronized with its orbital period around another body. For instance, our moon is tidally locked with Earth. For exoplanets, especially those orbiting very close to their stars, this means one side experiences eternal day while the other remains in perpetual night. This creates extreme temperature differentials across the planet's surface, profoundly influencing its atmosphere and potential habitability. These dynamic processes are critical for understanding how planetary systems evolve and the diverse conditions found on worlds beyond our own. Planetary migration is a fundamental process in astrophysics, revealing that a planet's initial formation location does not guarantee its final orbital position. Early in a star system's development, planets can significantly alter their orbits by interacting gravitationally with the dense protoplanetary disk from which they are accreting material. This interaction creates density waves within the disk, transferring angular momentum to the planet, causing it to move inward or outward. Furthermore, gravitational interactions between massive planets themselves can induce orbital shifts. This phenomenon is crucial for explaining many observed exoplanet systems, such as the hot Jupiters, gas giants found orbiting remarkably close to their parent stars. Such planets could not have formed in situ due to the high temperatures, suggesting they migrated inward from cooler outer regions. Even our own solar system is thought to have undergone significant planetary migration, with models like the Grand Tack hypothesis proposing that Jupiter and Saturn moved inward and then outward, profoundly shaping the distribution of smaller bodies and potentially influencing the formation of Earth. Tidal locking describes a celestial phenomenon where one side of a celestial body perpetually faces its gravitational partner. This occurs when the gravitational pull of a larger body gradually slows a smaller body's rotation until its rotational period matches its orbital period around the larger object. Earth's moon serves as our most familiar example. Its consistent face towards us is a direct consequence of being tidally locked with Earth. This process unfolds over billions of years, driven by the ceaseless forces of gravity. The implications of tidal locking extend dramatically to exoplanets. Many planets orbiting red dwarf stars, the universe's most common stellar type, are theorized to be tidally locked. Such worlds would feature an extreme climate gradient, a scorching day side perpetually exposed to its star's heat, potentially rendering it uninhabitable, and a frozen night side plunged into eternal darkness. The most temperate zones, and thus the most promising for liquid water and potential habitability, would likely exist along the narrow terminator line separating these two extremes. Understanding tidal locking is fundamental to assessing the potential environments and habitability of countless worlds beyond our solar system. Our Sun, a seemingly constant source of light and warmth, possesses a formidable and violent temper, manifesting as solar flares and coronal mass ejections. Solar flares are sudden, intense bursts of electromagnetic radiation originating from the sun's surface, releasing energy equivalent to millions of hydrogen bombs. These events travel at the speed of light, reaching Earth in approximately 8 minutes. More massive still are coronal mass ejections, or CMEs. These are colossal expulsions of magnetized plasma and solar material, launched into space at millions of miles per hour. While our planet's magnetic field largely protects us, these powerful phenomena can have significant repercussions on Earth. They are responsible for geomagnetic storms, which can disrupt satellite communications, impact power grids, and even pose risks to astronauts in orbit. However, these solar eruptions also create breathtaking auroral displays, illuminating our polar skies with nature's most spectacular light show. Understanding these solar events is crucial for space weather prediction and safeguarding our technological infrastructure. The solar wind is a phenomenon your teacher likely mentioned, but its profound impact is often understated. It represents a constant, high-speed outflow of energized plasma, primarily electrons and protons, continuously ejected from the sun's superheated outer atmosphere, the corona. These particles are not just passive emanations. They carry the sun's magnetic field, propagating it throughout the heliosphere at speeds ranging from 300 to over 800 kilometers per second. Upon encountering Earth, this torrent of charged particles interacts directly with our planet's formidable magnetic field, known as the magnetosphere. This interaction compresses the magnetosphere on the sunward side, creating a shock front, and stretches it into a long tail on the night side. While largely deflected, some solar wind particles are funneled along magnetic field lines towards the polar regions, where they excite atmospheric gases, creating the breathtaking auroras. Beyond its visual spectacle, the solar wind is a critical component of space weather, capable of disrupting satellite communications, navigation systems, and even terrestrial power grids during intense solar storms. Understanding this constant stream is vital for protecting our technological infrastructure in space and on Earth. Your teacher likely introduced gravity as a force, a pull between objects. However, one of the most profound revelations of 20th century physics, proposed by Albert Einstein in his theory of general relativity, is that gravity is not a force at all. Instead, it is a consequence of the curvature of spacetime. Imagine spacetime as an invisible, flexible fabric. Massive objects, such as planets, stars, and black holes, possess immense energy and mass, which literally bend and warp this fabric around them. This distortion creates a valley or depression in spacetime. Other objects, from satellites to light rays, do not fall into these objects due to a force. Rather, they simply follow the shortest possible path, or geodesic, through this curved spacetime. This fundamental shift from a force-based understanding to a geometric one underpins our modern cosmology, explaining phenomena like the bending of light around massive objects, known as gravitational lensing, and the behavior of black holes. Neutron stars represent one of the universe's most extreme states of matter. They originate from the catastrophic gravitational collapse of massive stars following a supernova explosion, squeezing an immense amount of material into an incredibly small volume. Imagine an object with more mass than our Sun compressed into a sphere no larger than a typical city, approximately 20 kilometers in diameter. This extreme compression results in mind-boggling density. A single cubic centimeter of neutron star material would weigh hundreds of millions of tons. These celestial bodies possess gravitational fields so potent they warp spacetime around them significantly, and their magnetic fields are among the strongest known in the universe, quadrillions of times more powerful than Earth's. Neutron stars are cosmic laboratories where physics operates under conditions impossible to replicate on Earth, offering profound insights into the fundamental nature of matter. Cosmic rays are not electromagnetic radiation, such as light or X-rays. Instead, they are incredibly high-energy subatomic particles, primarily protons and atomic nuclei, accelerated to nearly the speed of light. These particles originate from violent astronomical phenomena, including supernova explosions within our galaxy, and, even more powerfully, from active galactic nuclei in distant galaxies. Upon reaching Earth, these primary cosmic rays collide with atoms in our upper atmosphere, creating a cascade of secondary particles that shower down to the surface, with some even penetrating underground. While Earth's magnetic field and atmosphere provide substantial protection, a portion of these high-energy particles continuously bombards our planet, influencing atmospheric chemistry, potentially affecting sensitive electronics, and contributing to the natural radiation background to which all life is exposed. Beyond the vacuum, the universe possesses a surprising olfactory characteristic. Interstellar clouds, particularly dense star-forming regions like Sagittarius B2, contain detectable quantities of ethyl formate. This specific organic molecule is directly responsible for the distinct aroma of raspberries. Furthermore, it contributes significantly to the characteristic flavor profile of rum. This means that vast expanses of the cosmos carry a faint, ethereal scent, subtly hinting at notes of both fruity sweetness and aged spirits. It challenges the conventional perception of space as an odorless void, revealing a more chemically rich and unexpected